Okay, so we're finally on our last case for the characteristic equation of a second-order linear homogeneous ordinary differential equation. And remember that simply means that both p and q are constants and it is equal to 0. So this is the specific type of second-order differential equation that we're dealing with. Okay, so remember that the characteristic equation derives from when you guess that the solution to this differential equation is somehow in the form of y equals e to the rt. And so when you substitute in y for that into this differential equation, you get e to the rt, r squared, plus pr plus q equals 0. And so since e to the rt can't equal 0, this must equal 0, and you end up with a quadratic. And a quadratic, of course, has three possible cases for the solutions. One is that you get two real roots. The second case is that you get no real roots, and the third case is that you get one real root. So today we'll be exploring the third case, which is when you're trying to solve this thing and you only get one real root for r. And obviously you need two fundamental solutions in order to formulate a general solution, so we're going to have to figure out a way to get that second solution. Okay, this is definitely the most algebra heavy and convoluted derivation out of the three cases, so I'm going to try and make it as simplistic as possible and not bore you for too long. Okay, so let's review the quadratic formula. So when you try and solve for this thing, you get something like this, where so this equals 0, so basically this plus or minus thing is out of the question, and you only have one real solution, which is negative p over 2. And now, okay, so basically we're going to have to do something. We're going to have to do something to guess another solution. So first I'm going to set r as equal to negative p over 2. Okay, because this is the one real solution that we have so far. So this is the r, solving for r right now. We only know that r equals negative p over 2. Okay, so what we're going to do to try and solve this thing is called variation of parameters. Okay, so what variation of parameters basically is that you know that when you have this one solution, you can stick any constant in front of it and it should still work, right? So let's say y equals e to the rt. Let's say that was the solution to some differential equation. You know that if that is the solution, then negative e to the rt, 2e to the rt, 3e to the rt, all those different constants in front of the formula, those would also work as solutions because of the fact that the initial condition is what determines the constant. So theoretically, any constant could solve the differential equation. Okay, so what variation of parameter does is it assumes that the constant multiplier in the solution to the differential equation is actually a function. And not a constant. So I'm going to demonstrate this with what we have here. Okay, so instead of guessing that y equals e to the rt, we're going to guess that y equals some v of t e to the rt. So we're going to replace the constant in front with a function. And then so now what we're going to do is, before when we substituted in e to the rt into this differential equation, this is what we got. Well, now we're going to substitute in y equals v of t e to the rt into this differential equation and see what we get. Okay, so obviously this is going to be slightly more difficult simply because when you take derivatives, you're going to have to account for the product rule now. So we're just going to first figure out the derivatives. So y double prime equals v double prime t e to the rt. Okay, actually this is a bad idea. We should figure out the first derivative first before the second derivative. Okay, sorry, got too excited there. Okay, so we're going to figure out the first derivative with the product rule. So first derivative, so we're going to take the derivative of the first function times the second function added to the derivative of the second function times the first function. So the derivative of this is r e to the rt, so we're going to pull the r out in front and then multiply that by e to the rt. Okay, so now we're going to take the second derivative, which simply deals with taking this derivative again, the derivative of this again. So the derivative of v prime t e to the rt. So take the derivative of the first function, v double prime t e to the rt, and then take the derivative of the second function. So again, it's r e to the rt, and I'm going to pull the r out in front. So and then take the derivative of this section. So the r is simply a constant, right? So I can just like pull that out, and then we already have the derivative of this, which is this whole thing. Okay, and then I can simplify that. So again, if anyone is confused as to what I did, I just took the first derivative of this thing and took the second derivative of this thing, because that's going to be a lot easier to know and to have when we're substituting this stuff in for the differential within the differential equation up here. So now I'm just distributing. And that is what I get. Okay, so now we're going to substitute in these two for the general form we have up here. So we're going to substitute in y double prime and y prime into this thing up here, and y, of course. Okay. This is going to be a long expression. So we're going to have okay, so that is y double prime, and that is substituted in for this term, and now we're going to have p times y prime, so plus p times y prime, which is over here, and then plus q times y, which is simply this thing. So now what can we do? Well, we could maybe factor some things out, right? So we see that there are lots of common terms over here. We have a common term of the v prime in many terms within this equation, and we also have the common term of v within many of these terms in the equation. So we can just combine like terms, factor out stuff, and then see what happens. So we combine like terms. Okay, so that's the only term with a double prime, and then we can group all the terms with 1 prime. So here's one. Here's another one. And here's another one. And yeah, I think that's it. So, and then we're going to group the ones with just v of t. So here's one. Here's another one. And then here's the final one. And so that is what we get when we combine like terms and we factor it out. And remember, this whole thing is still just this thing substituted in for y in the general form. Okay, so what do we notice here? What do we notice about this term? Well, we notice that this is r squared e to the rt plus p r e to the rt plus q e to the rt. So each of these has an e to the rt term. Now let's just ignore those terms for a second, right? So if we just ignore those terms, we have r squared plus pr plus q. And we know what that equals, right? So up here we have that e to the rt factored out, and then r squared plus pr plus q equals 0. So this thing is the same thing as this thing. So we know that this whole term equals 0. So we can just cancel this thing out, right? Equals 0. So we just got rid of this entire thing right here, and we're only left with this. Okay. So recognize that this and then we can further simplify down to just the first two. So this is 2r e to the rt because these two are the same thing. Okay, so now this is what we have left, which looks a lot more manageable than what we had before. Okay, so now I guess what we're going to do is we're going to make a substitution. Okay, so substitution, we're going to say w is equal to y prime. Or not w, okay, my bad. W equals v prime. V prime, not y prime. We make the substitution, then all these second order things go away, and we just have the whole thing as a first order, and we know how to solve that. Okay, so we're going to make that substitution right now. And so we're going to have w prime t e to the rt plus w t 2r e to the rt plus p e to the rt. Okay, and then this whole thing is equal to 0 because, like I said before, we're substituting into this thing, which equals 0. So I didn't put that there over here, but this thing equals 0. This thing also equals 0. Okay, so this whole thing equals 0. And we can see that there's an e to the rt term in every single term. So we can just divide that out, and we're left with okay, now let's look at the 2r plus p. Okay, we said here before that r equals negative p over 2 because r was the real solution that we got from the quadratic formula. So 2r is going to be negative p, right? And then if we have a 2r plus p, then this thing is just going to be negative p plus p, which equals 0. So this thing equals 0 again. And isn't that amazing? This part cancels out. So now we're left with the simplest differential equation to ever exist, w prime of t equals 0. So of course we can integrate that and get w of t equals c. And then remember that w was actually b prime, so then we can remember that over here. So b prime of t equals c, integrate again, b prime of t equals ct plus d. Okay, so we've got that v of t equals ct plus d. And again, we're just going to assume that these constants are products of the initial condition and don't really matter, so what really matters itself is the form of the function. So the form of the function is a linear, so the simplest linear we have is t. So since v of t equals ct plus d, and we're just going to assume that it takes on its simplest form of t, then over here, this is found to equal t e to the rt, because v of t, like I said, was ct plus d, and since the constants we're going to assume come later with the initial conditions, we can just ignore those for now and just say it's t. So this is what we have gotten from the variation of parameters. So our first solution was y1 equals e to the rt, in which rt or r equals negative p over 2, right? Because that was the real solution. So our second one, which was derived from variation of parameters, is t e to the rt. So therefore, our general solution is going to be c1 e to the rt plus c2 t e to the rt. And this r is going to be also negative p over 2. So this is the general solution for case 3. And like I said, I could take the Wronskian and prove to you that it is the general solution, but I am not going to do that, and hope that you will trust me when I say that it is a general solution.